This is the Chapter 3 whiteboard lecture on solid solution. This lecture covers the PowerPoint slides number 20 through 24. Minerals have a definition, and that includes these characteristics. They have to be naturally occurring, they have to be inorganic, they have to be solid with a crystalline structure, they have a set of physical properties that's similar to all pieces of a mineral, and they have a set chemical composition. That composition can vary within some pretty strict limits, and that's what we're going to talk about today, because there are some common minerals in the rocks that make up the crust that have this kind of solid solution. So a variation in chemical composition in a mineral goes by two different names. It can be called an ionic substitution, which is what a chemist would call it, but if you're a geologist, you refer to it as a solid solution. We're more familiar with liquid solutions because we can easily mix two liquids together, which is what makes a solution. So we're going to use that as an analogy to talk about what a solid solution will mean for a mineral. So in the graphic below, I've got two end members. Those are the two liquids that you mix together to make your solution. So one of our end members is chocolate syrup and the other is milk. And we mix them together to make chocolate milk. We can put just a little bit of chocolate syrup in our milk, make kind of a milky chocolate milk, or we can put more chocolate syrup in our milk and make a more chocolatey chocolate milk. So there's actually an entire range of solutions here, liquid solutions, from pure chocolate syrup all the way to pure milk. You could have just a drop of chocolate in your milk, or you could have just a drop of milk in your chocolate syrup, or any combination in between that. And those are all chocolate milk. They're different solutions, but using the same two end members. So for minerals, we are talking about solids, but when these solids crystallize, sometimes their chemistry can vary just a small amount in specific ways. So we're going to use the example of olivine because it's a common mineral in the crust. Olivine has two end members. One end member is an olivine crystal where it is a silicate and magnesium. So SiO4 is the silicate part, and then we have the magnesium. And there are two magnesium ions for every one silicon to four oxygens. The other end member is an iron-rich olivine, where we have iron instead of magnesium along with the silicate. But it turns out that in nature, olivine can sometimes take up some iron and some magnesium, and there can be different proportions. Sometimes there's a lot of iron and very little magnesium. Sometimes it's 50% of each. Sometimes it's a lot of magnesium and very little iron. Depends on the conditions in which the olivine crystal is growing. The reason that we find this interesting is because this can help us understand the magma in which the olivine crystal grew. So how do we write that when we are talking about olivine? We don't use the terms forsterite and fayalite very often because most olivine lies somewhere along that spectrum of solid solutions. Well, what we do is we use parentheses in the formula, and we write it so that we have magnesium and iron both within the parentheses. And then we have the subscript 2, which tells us there's room for two atoms there, but we're not sure whether both of them are magnesium, both of them are iron, or there's one of each. And then that is connected to the silicate part. So whenever you see parentheses in the chemical formula of a mineral, what it's telling you is that those ions that are inside the parentheses can vary just a small amount.